Sorry about that.
Okay, so you don't have a title slide.
I do, but I'm not going to show it first.
But you're not going to show it. Okay, so we have to guess. So
so it's going to be on development of staircases in forced shallow water turbulence by topographic forcing, but the actual title will come in the next slide.
The official title is Jet Dynamics in Topographically Forced Shallow Water Planetary Atmospheres.
That sounds better.
So, David.
Thank you. So first, thank you to the organizers for inviting me here, and I apologize for being totally unresponsive. So my talk came very late into the program in terms of the title, but I'm lucky to get here because of teaching was crazy until now. I won't waste any more time on that, but I'm now in research mode. So this is going to be work that I've been doing with Richard Scott. You can play the movie now. So this is actually a spherical shallow water simulation viewed from 30-degree latitude downwards. The North Pole is the top of the figure there. You can press the red thing? Okay, good. So this is a beautiful example of formation of jets. You're seeing the relative vorticity, red being positive, blue being negative. The white bands that separate these things are extremely sharp, highly variable. They might be zonons, probably like the previous talk. So I also thank Laura for introducing almost every concept I need for this talk. But this is a long simulation that runs for, the time doesn't really matter, but in terms of days, 30,000 equivalent days for the atmosphere. It's a situation forced or damped by thermal damping, weak thermal damping in this case of 500-day time scale. There's a forcing going on here, which I believe is a broadband topographic forcing, which I'll describe later, which is time dependent. So it's like thunderstorms underneath, trying to mimic what might be happening in the gas giants. But the most conspicuous feature that you see emerging here are these sharp jets. These white bands here are regions of intense zonal velocity, not even zonal velocity, they're a long jet velocity. The sharpness of the red to blue here is achieved by using a special numerical method based on originally contour dynamics. It's called Contour Advection, and it allows basically one to simulate these flows and achieve extremely sharp vorticity and potential vorticity gradients in these flows, and that picks out these jet structures very clearly. In a spherical simulation, there's at least 1, 2, 3, 4, 5 jets that appear for the parameters. I'll come to the parameter space later. It's complicated. This is no longer a barotropic vorticity equation on a theta plane. Here it starts again. So very rapidly from early days, the forcing generates, organizes itself, as we've seen time and time again from the classic work of Ryan's years ago to the current day. We see this persistent formation of jets based on what's just random isotropic forcing. And the essential ingredient, as Laura mentioned, and others too, is basically the presence of a planetary vorticity gradient. Here, the going from the South Pole to the North Pole. What's more complicated in this example compared to previous talks is that we're now considering the full shallow water equations. There's some kind of stratification effects by having a free surface on the flow. Interesting, there's a little vortex sitting there, a cyclonic vortex moving around the North Pole. The thing that's different maybe from what you might see from observations of Jupiter, Saturn, and other planets, that the Jupiter one in particular, is that the waves that are on these interfaces tend to be apparently of larger amplitude. I'm not claiming this is the model that explains the gas giants. It's only shallow water equation, single layer, and probably has not enough parameters and complexity to be able to describe what's taking place. Certainly not the vertical structure of the jets in the atmosphere, but it's still remarkable that even a relatively simple model like this can form things. And you can even see possibly evidence of vortices here, anticyclonic vortices moving around in bands. So, and also here cyclonic ones. So you get features that you're seeing on planetary atmospheres, yet in an incredibly simple model. And this is a unique situation where we've done proper topographic forcing, which people have been arguing for some time as the natural mechanism to try to investigate here. yet most people force this using so-called balanced or vorticity forcing, and I'll talk about that. So I can switch now to the actual talk, which I may not have no time to give, but I wanted the movie I thought was more impressive than the still, so I thought that was more important. So this is work with Richard Scott and Mahdi Jalali, who's now in London, and it was done over the last few years, and this doesn't seem to work anymore. Oh, there it is. So we basically conducted a bunch of simulations of shallow water dynamics in spherical geometry, forcing to see what happens. And this is an old, well-studied problem, going back to the famous Scott and Pavoni paper, which looked at the formation of jets on the giant planets, trying to simulate parameters that were using a shallow water model to try to capture the kinds of phenomena that are occurring there. And for various planets, the Jupiter on the left, Saturn, Uranus, Neptune on the right, they were basically running a shallow water model and showing that in potential vorticity, probably potential vorticity anomaly, the way it's being plotted. No, it could be potential vorticity. It's hard to tell what they've done here with the color scale. But you see the emergence of jets appearing here, although they're very diffuse. Of course, you can give them some credit. This is back from 2007 and earlier, so simulations were, you couldn't conduct a shallow water simulation at very high resolution at that time. But the key thing that they talk about is that their forcing is designed to represent what they consider the actual forcing by overturning convective systems or other random motions generated by a deep and turbulent interior. So they want to emulate the forcing that they think might be taking place there. We don't really know what's taking place there. There's lots of evidence of lightning and thunder, or well, we don't know thunder, we can't hear Jupiter, but we know we've seen lightning everywhere, so we know there are lots of storms on Jupiter in the lower atmosphere. This could be generating the forcing that we're seeing in the middle to upper atmosphere that we see in the cloud patterns. And so it sort of begs the question, what happens if you put that kind of forcing in a model? Well, despite the fact that they say this, they actually didn't do it. They actually were looking at a simpler form of vorticity forcing where you directly force the relative vorticity by stochastic force. This is nice because it doesn't generate much divergence. And as everybody knows, doing GCMs, divergence is the menace for all kinds of simulations. It leads to model blow up. It's messy, generate inertial gravity waves, hard to control what happens when that happens. So people don't like to really force things by, say, moist convection or some kind of topographic forcing. So Adam Shulman was the first one to consider this. He looked at a sector model on a sphere, some simplified version of the forcing, didn't really do a full planet study, but some elements of the formation of jets were seen in this study, and it's the same special issue on the subject. To get to the problem before I run out of time, so we're going to consider of course it's a very great idealization. Sorry, I don't know what I'm doing here. There we go. Now I know the buttons do different things here. So we're considering a fluid region which is sitting over a variable topography. So the green is it's not the real shape of the underlying surface, but this is of course greatly exaggerated scales. The atmosphere is really not that thick. But to give you an idea, it's a shallow water flow on a spherical surface. The planet's rotating at some fixed rotation rate, which will non-dimensionalize so that time will be in units of days, if I don't say that later on. For the equations are dead simple. They're just the usual shallow water equations with the usual velocity, Coriolis frequency, the height of the thickness of the fluid, h, and b, which will represent the bottom topography. And b for us will be both space and time dependent. So it won't be a fixed topography, but it will be some kind of oscillation induced by convective activity, which we'll consider isotropic, which is probably a very bad assumption, but this is already a very parameter-rich problem, which is part of the reason we can't move from crawling onto walking. We're still doing shallow water dynamics years and years later because we don't really understand the full behavior of even this simple system. It doesn't look like there are many parameters in this problem, but there are more than you think. In the height equation, we also introduce thermal damping. So this is a big difference from the previous talk where there was Ekman or Rayleigh damping, a very different kind of mechanism for damping. Here, the thermal damping is considered more realistic for the deep atmospheres of Jupiter, Saturn. So we're going to use the thermal damping like Scott and Polvani did and others in shallow water simulations before. So regarding the topography, so we're thinking about the topographic forcing as being some kind of forcing by convective storms everywhere that are forcing the layer that we're seeing. And we're going to take it to be similar, well, having a spectrum, either a narrowband spectrum or a broadband spectrum. So here's an example of the forcing spectrum for a particular peak wave number, KB. So I'm thinking about a spherical planet of radius 1. We can do that here. So this is wave number 32 forcing on that. So fairly small scale forcing. And in a broadband forcing will have this form, some kind of distribution like this, purely cooked up to be nice. But the actual details of the forcing don't really matter, as we will show in a minute. We can either consider broadband forcing or a narrowband forcing about that wave number with a couple of wave numbers either side of it. Almost everyone to date has considered narrowband forcing, and narrowband forcing is not really the kind of forcing that would apply to a localized convective storm. Any single localized storm would produce a very broad range of wave numbers. And so superposition of these, likewise, unless they're organized in a particularly nice pattern, would also produce a broadband spectrum. So we favor broadband forcing for that reason. Thermal relaxation, so it's thought to be, it's basically a very simple model of radiative damping in the atmosphere, and it's thought by Thompson and McIntyre to be more realistic for than Ekman damping for the gas giants. Okay, so regarding parameters, so we can absorb the gravity G into the mean thickness of the fluid layer to define a short scale gravity wave speed, which is this parameter C. And then you can recast the equation in terms of a dimensionless height anomaly, which I'm going to call H tilde, which is no units at all, of course, and then a dimensionless topography B divided by H. When you do that, there are only a few parameters that are left. We can take basically scale things by length scales by the radius of the planet and set the rotation period to be 2 pi so that a unit of time is 1 day. When you do that, then 4 parameters appear. In fact, there are more than that, but I'll come to that in a minute. The main parameter is the Rossby deformation wave number. This is again a new parameter compared to the previous talk. Here now we have to consider the fact that a shallow water non-barotropic system also has a further length scale given by the planetary vorticity, 2 omega at the North Pole divided by C. We also have a thermal relaxation time tau, the amplitude of the topographic forcing BRMS, and a forcing decorrelation timescale TB, which is described in some complicated stuff here, but we're basically following the same process that Scott and Polvani introduced earlier in terms of adding a time-correlated field as a forcing. We're forcing using topographic forcing, and topographic forcing, of course, has a multitude of parameters. It doesn't have to be one particular form, and well, I'm not saying that the type of results we get will be completely universal in terms of different types of forcing you can apply, but we have tried broadband and narrowband, and you get similar things. So this is what the forcing looks like. The forcing, this is the topographic forcing at 3 different times, so it's varying in time. The top is narrowband, and the bottom is broadband. And if you're given 2 pictures like this, you'd probably struggle to figure out which one looks different, which is really broadband and narrowband. But so there isn't much difference in terms of the structural form. You might think that this is a little bit more patterned, more regular than the one down here, and that's really the difference here. But the point is that over this time, the topography is constantly changing, but slowly changing in time. This is equatorial view, although it looks the same in all directions. Okay, so the numerical model, I don't have time to talk about it much, but it's based on contour dynamics originally. It's called the combined Lagrangian advection method. We directly evolve potential vorticity. We do this on a set of contours. In this case, could be hundreds of potential vorticity levels. The number of contours that may exist at any given time might be in the order of millions. The number of points on these contours might be on the order of tens to 100 million. So it's a very complex simulation in principle, which allows you to capture these sharp gradients. We use a trick that avoids the North Pole, which uses half latitudes. This is something that Ali Moheb Al-Hajj, who is here as a PhD student years ago and worked with me many years, he came up with this idea of using this for the shallow water equations in the Contour Advection model. And then we use FFTs in longitude and compact differences in latitudes, or even FFTs around great circles. I'm not going to give any details of the method. If you're interested, these are published papers on the method, and I can give more details. So alongside potential vorticity, we evolved the divergence and what's called the acceleration divergence, this divergence of acceleration, in place of the dimensionless height anomaly and the velocity. And this basically is done from a lot of experience over many papers, better representing the balance part of the PV control dynamics, as well as the gravity waves that emerge in the system. We initialize the flow starting from a state of rest, but with topography using the nonlinear balance relations that result from setting these partial time derivatives of these variables to zero. I haven't written down the equations, but they're a set of two coupled nonlinear equations, along with the definition of potential vorticity that allow one to recover all the variables. So this is a kind of generalized balance method. Okay, so then I'm not going to show you all these parameters. I'll probably easily run out of time. In fact, I only have 7 minutes and 52 seconds left. So, okay, so we investigated a range of Rossby deformation wave numbers, with the higher range being characteristic of the gas giants. Different thermal relaxation periods. We don't really know what that parameter should be, honestly, and then different forcing amplitudes and different decorrelation timescales. We use what looks to be extremely modest resolution of 256 by 512, but the resolution is effectively 16 times that in each direction. And there's some work with Steve here years ago in MHD context. We run simulations out to a very long time, and we resolve explicitly the gravity waves. So we're not trying to filter anything. Okay, the effect of the forcing spectrum first. So what we've done is shown 3 images of the flow at 3 different times. The top being, this is relative vorticity field again. Almost all cases show relative vorticity. And the top is narrowband forcing, and the bottom is broadband forcing. And there's not a huge difference in the outcome of the flow. From early on, the flow organizes to a series of jets that maybe have zonon-like features appearing in them, very wavy structures with the equator being very distinct. This is the same thing, but look down from the North Pole. Top is narrowband, broadband here. You can see this cyclonic vortex near the North Pole. Much more disorganized structure near the polar regions, which are consistent with observations, actually recently, of Jupiter. Jet drift, jet migration, beautiful. So we see that in some examples. So this is in a case where, again, the narrowband, broadband, very clear migration poleward. We've never actually seen equatorial migration in any of these, but then it may be the type of forcing we're using, or parameter regime we're looking at. We've covered, as far as we can, all the parameter space, but we often see poleward drift of the jets. Okay, so there's no qualitative difference. Polar regions are highly dynamic, and jets are persistently wavy, but they're very sharp. Well, Scott and Pavani have commented many times that they tend to find steady jets, although there's some weak drifting taking place here, but most of the jets they show in these Hofmüller diagrams show persistent jets lasting for long times. And many papers have followed this study by using similar kinds of forcing mechanisms and finding steady jets. And then you might think, well, is topographic forcing appropriate? So we were finding jet drift in these simulations. And as I just remind you here, Scott and Pavani themselves thought that we should be looking at some kind of topographic type forcing, okay, even though they didn't do it. And I love this cartoon better than any cartoon in the New Yorker, probably my favorite one. Like, is everybody following the same kind of thing, going off the cliff? But another more worrying thing is that with the climate change taking place, is everybody basically saying, well, let's ignore it and we'll go over the cliff eventually. That's another political message there, but forget that. So deformation wave number, probably the most important parameter in this system. The two important parameters are deformation wave number and the thermal damping rate. Remarkably, with the deformation wave number, so I'm showing now two cases. The top just a low deformation wave number, so this you'd expect a small number of jets. The bottom is a high one, and actually, if you look at the vorticity field shown on the left here, which I've been showing up to now, there's not a lot of difference between the number of jets that develop. Maybe a few more at higher KD. This shows the divergence field and the height field in this case, so no discernible patterns there. Notably, the divergence is comparable to the vorticity in amplitude. And again, jet drift appears, although it's a little less conspicuous at KD 25 on the Hubble diagrams. The right-hand side shows the PV gradient, the mean PV gradient in latitude, which probably better shows the sharp gradients developing here. Okay, so as KD increases, both jet spacing and intensity decrease, and the large KD appears to favors the development of a strong equatorial easterly flow. It's seen in many simulations before. Only the high latitude jets drift polewards. There's some difference from the previous work or previous simulations are showing, and divergence motions are greatly suppressed as you go to larger KD. I'm probably only going to be able to talk about thermal relaxation. So with thermal relaxation, so now contrasting rapid relaxation with slow relaxation in the development. This is again the final time here. With long time scales, the jets are a bit sharper. They're a little bit less wavy here. Hubble diagrams now, interestingly, show persistence of much more steady jets at late times. It's one of the few examples where in cross-parameter space we find steady jets. And here they are. The jet structure sort of similar to the, oops, which way am I going here? No, wrong way. There we go. So you see in the potential vorticity, you see a clear staircase structure developing at late times, and the corresponding zonal velocity field corresponds to the steps that are seen in the potential vorticity field by the balance you expect here. I'm going to skip all these results because there's clearly no time. I only have a minute 36 seconds, is that right?
Well, you got a few minutes grace because you started a bit late. So.
All right, well, I'll just go to the conclusions. Since, I mean, forcing amplitude, that's kind of interesting as well, that you can look at very weak amplitude at the top and stronger amplitude at the bottom. For weak amplitude forcing than you do at very late times, it's huge simulation times, you start getting the emergence of equatorial jets. And I won't go to that, but I'll just go to the conclusions. So we revisit jet formation. The vorticity forcing by Scott and Pavani, and you said that by many of the since mainly excites balanced PV controlled motions, Rossby waves. So they didn't get many divergent motions, and the divergence could be part of the reason for the jet drift. Of course, the previous talk also found jet drift without divergence, so that's sort of open as an idea. We use topographic forcing like Schumann. Such forcing often leads to polar jet drift, but this exception is either weak forcing, which I didn't have time to really go into, but the weakest forcing we applied for very long times seems to produce steady zonal jets, or low to moderate Rossby deformation wave numbers, which actually aren't observed on the outer planets. The Rossby deformation wave numbers more like 30 to 40, we think, on Jupiter. at that, there seems to be jet drift taking place. Now, it's not clear that over a 20-year period where we've seen the Jupiter atmosphere twice, whether that's a long time scale or a short time scale, but I'll leave that open. I'll stop there with -8 seconds to go.
Okay, that's good. Time for a question.
Yeah, very nice. So in general, what do we know about the vertical structure of the jets, of like say Jupiter's jets, and what have people done, like even just the orientation of the jet with respect to rotation vector or something like this? Like, what do they look like in the
Well, there are observations that there's a limited observation of something being dropped into Jupiter and measuring vertical structure, and there are things that you can infer about the vertical structure of these planets. And the thought jets, I mean, Peter here would tell you much more about this than I would, because he knows much more about the vertical structure of jets. But they do extend deeply into the planetary atmosphere. I think on Saturn, they're much deeper than they are on Jupiter in terms of a fraction of the radius of the planet. It's unclear whether a shallow water model on its own, in fact, I would argue that a shallow water model on its own is probably not the right model to be doing this, but it's surprising it captures as much as it does. People otherwise use these deep convection models where you get like these booster columns that might organize themselves, and both deep and shallow water systems produce jets, forming them, which leads to an open controversy that's never really been resolved in this area. We just don't know enough about the vertical structure. But what should be done is to do simulations that are midway between this very idealized one and the full GCM. Why not do 2-3 layer shallow water? And so that's what I'm going for next. Yeah. Yeah.
You looked at in more details into the polar dynamics. Have you seen those clusters of vortices around the central one?
Yes, so the polar dynamics is interesting because if you stare at the movies for a while, you start seeing like the hexagon or whatever. You can see all these different kinds of patterns that are forming, and are they? I mean, these simulations look like they're fast and fastly evolving, but for different parameters, it could be that they persist for long periods of times. It's not clear. And if we flew back to Saturn and look at the polar region again, would it look different again next time you go there? Is it evolving on some time scale? We don't know. But yeah, the polar regions are much more disrupted, which is now what we see now on Jupiter in particular, that the polar regions are full of like a zoo of vortices.
You have 8 at the North Pole and 5 at the South Pole or something.
That's right, yeah. So that's
and very regularly organized. So
that's right.
You have ever seen that in your?
Well, it changes. So if you look at the movie, and I'm negative 3.14 seconds, whatever minutes. So I can't show it to you yet, but I can show you on my own laptop that you can see these patterns emerging at the polar regions, but they change. So you have wave number 3, 4, 5, 6, but it tends to be a low number of waves that you see forming. But the structure of the polar vortex in the atmosphere also is showing wave 2, wave 3 oscillations, typically in the winter.
Maybe it relates back to Mary-Louise's question. So a big criticism in the past of shallow water was that they don't get the direction of the equatorial jet. Correct. So by putting in beta forcing, are you able to get simulations where the equatorial jet is actually prograde instead of retrograde?
You get typically retrograde jets, no jets, and occasionally poleward or prograde. So you do get prograde jets with some forcing. I've seen both, but predominantly retrograde. But there are cases, some which are shown here, where there's no discernible jet structure, that the whole region is homogenized without any kind of well-organized structure at the equator. But I think the most frequent observation with topographic forcing, and it's because of thermal damping, which is probably not appropriate as well, and the shallow water consumption really is breaking down very close to the equator. There are many problems with the shallow water model near the equator. The vertical structure is then probably very important, which is not captured in the shallow water model. Having done that, having said all those things, you still can get situations where you can get prograde or retrograde jets. But I wouldn't put much credence into what takes place at the equator in a shallow water model.
Just a comment. You raise the issue that the jets that we observe on Jupiter and Saturn don't meander as much as the ones in most of your.
I don't know, but it looks like these are meandering too much compared to what people. A lot of people argue that they shouldn't be meandering at all. Look, 20 years later, you go back and you look at Jupiter and you see the jets in the same places.
Yeah, but if you zoom in, I mean, you do see small scale meanders, but they're.
Oh, you mean the actual?
On a smaller scale than
Right.
I think was apparent.
Right.
Based on the,
And that could be related to the deformation length, which is smaller, which you get more oscillations. So that's yeah. So I guess what's remarkable in these simulations is that you make a movie of them, you see them dancing all the time. These waves are persistently there. You never get these nice, clean, sharp gradients that are zonal, but they're very
even
wavy.
with a very weak forcing.
Even with the weaker the forcing is, you still get the persistent waviness. And that's, Richard Scott and I looked at this in the beta plane case, and it didn't matter how small you made, we made this anosopy parameter like 12, huge number, and you still get very wavy jets. Yeah.
So you motivated using the thermal damping because it's more realistic. If you had used an Ekman damping, how do you think the results would have changed?
Well, more people have done Ekman damping probably in, I guess, I think, I should be able to answer this, but I don't know if I can remember people doing Ekman damping in spherical geometry full global simulations. So I don't know if it's really been done. I think almost everyone doing shallow water simulations trying to apply it to these situations have only thought about the thermal damping case. So I guess that's an interesting question. I mean, the Ekman damping might be relevant to the oceans, but the oceans are enclosed basins with topography and coastlines, etc. So it's a different problem. I wouldn't know how to answer that.
How it manifests in the non-conservative terms in your PV equation. One involves the curl, the other.
Yes, so in the PV equation, you get a term which is kind of like a hypodiffusion because of the thermal damping, whereas with Ekman damping, it's sort of like a linear Rayleigh drag, and that's the difference. But it seemed like we get jet migration and drift in both cases. So the actual details of the damping mechanism may not be that important for that.
Okay, I'm conscious that tea is waiting outside, so I think we should probably wind up the formal proceedings now. But of course, our speakers are around if you want to nobble them with your favourite question. So shall we thank David and Laura?